Hello, I'm Hyeok from Northwestern University. Today I'm going to introduce Erie, a declarative grammar for data sonification on behalf of my colleagues. Before the grammar, let's do an exploration of an exoplanet with the James Webb Space Telescope. James Webb Space Telescope detects infrared lights coming from space entities like stars and planets. An interesting kind of observation it makes is detection of water spots from exoplanets. So a planet like the Earth has an atmosphere that blocks some light coming from its star, like the sun. By measuring the amount of such blocked light by different wavelengths, scientists can detect water spots. So now I'm going to play a sonification that represents such light blockage observation of an exoplanet called WASP 96b, and let's guess how many water spots were detected from this exoplanet. The answer is 4. This is the original data, and the water spots here are noted as H2O. So what's data sonification? People here might be more familiar with data visualization that maps data variables like precipitation or response rates to visual variables like bar heights, map colors, etc. Similarly, data sonification maps data variables to auditory variables like pitch, time, duration, and volume. Sonification has a variety of applications such as data storytelling, scientific observations like one I showed earlier, or more traditional cases like Geiger counter. Museums can also use audiographs to produce more immersive experiences and data accessibility for blind people. However, doing sonification research as well as production is quite challenging. Practitioners need to understand an auditory space such as physical properties of the wavelengths and relationships between detuning and duration, etc. And on top of such knowledge, they need to know how to engineer sounds, like how to connect different audio nodes. Even very simple designs are not that easy to understand or represent. Therefore, to help data workers to reason more around their data instead of these realization techniques, we need a data-driven approach to express sonification design. Current practices of data sonification rely more on ad hoc solutions and offer limited expressions. We did a preliminary survey of online tutorials and toolkits out in the world. Online tutorials tend to focus on instructions for a specific design goal, like a discrete data points to pitch. So it is hard to reuse and reapply or parameterize them when circumstances change. Next, existing toolkits only provide compartmentalized support for different techniques and expressions. So it is difficult to mix and match different instruments and auditory channels, and this are just quite a big challenge for researchers and practitioners to explore diverse designs. So we need an expressive and extensible sonification toolkit. One quick approach could be just to sonify a visualization, which could be easier for visualization authors just to adopt. However, I underscore that the same visual encodings may not mean the same auditory encodings. We don't even know whether it is true or false. To motivate this with an example, after fitting a regression model, we want to check the fit of the model using residuals. Typically, we use a residual plot and a QQ plot. Residual plots are for checking whether residuals are distributed randomly and evenly on both sides of the zero line. And QQ plots are for checking whether residuals follow a normal distribution. Both charts use the same encodings, X and Y positions. However, what we decode are quite different. For residual plots, we want to decode how much residuals are deviating from the zero line. On the other hand, for QQ plots, we want to see the deviation from the diagonal line. So just mechanically mapping X and Y to certain encoding channels may not be the most ideal conversion. Therefore, we need a sonification toolkit that is independent from visualization designs. In consideration of these challenges, I introduced Erie as an expressive, independent, data-driven, and extensible toolkit for data sonification. To show how to specify a sonification design using Erie, I'll present a walkthrough for sonifying an auditory histogram. This auditory histogram maps to the time in seconds, and the count of it being to the pitch of the corresponding sound. First, I'll play the auditory scale that describes this histogram, and speech will be really fast.
A histogram of miles underscore per underscore gallon variable. This stream has the following sound mappings. The miles underscore per underscore gallon, bin, is mapped to time. The count is mapped to pitch. The minimum value 1 is mapped to. And the maximum value 98 is mapped to.
And then I'll play this sonification. Erie specifies a sonification design in terms of data, tone, and encoding. First, data to sonify. In this case, I provide the URL of this cars dataset. And then to make a histogram, we need to set some bins and get the count per bin. Next, before encoding data points, we need to set what kind of tone or overall quality of sound to use. As histogram is a discretizing technique, we use a discrete sound where auditory characteristics change abruptly over time. Then we map the data points to auditory channels. The bin start point is mapped to the startup time of the corresponding sound, and the bin's end point is mapped to the end of the sound. Lastly, the count per bin is mapped to the pitch encoding. Then this design spec is first compiled to an audio cue, which is a schedule information about when and how to play the sounds and which way. And then this audio cue is rendered as sonification sound like this. For rich data stories, one can concatenate multiple sonification streams by sequencing them to be played one after another, or by overlaying them to be played all together. Multiple sonification streams can also be generated in a data-driven way, which is called repetition. Those repeated streams can also be sequenced or overlaid. Erie's design spec, compiler, and player supports some extensions. For example, external audio files like water drop sounds that I had in my first example can be sampled into sonification. In addition, a developer can create and attach audio filters with some custom encoding channels. For example, I put a simple distortion filter on the auditory histogram we heard earlier, which makes a bit more sharper sound like this. As a declarative grammar, Erie can support building sonification applications as well. We replicated audio narrative and chart reader. Some merits of using Erie include reusability and customization of design. And we basically use the same design spec for audio narrative to chart reader. And then we added some personalization options like auditory encoding choices. With all these capabilities, there are lots of potential future research that Erie can support and facilitate. We can do empirical research in sonification perception by systematically parameterizing stimuli and using a larger set of possible expressions. We can build user applications with sonifications more easily. We can also support users to personalize and customize audiographs according to their preferences. Erie is currently a bit too low level, so we need to work on accessible creation of sonifications and implement Erie on other environments like R and Python. This is the end of my presentation. Thank you so much for listening. You can make Erie via GitHub repo, npm repo, documentation, and online editor with an example gallery. Thanks so much.